In the last video, we learned some rules for how to write the SPD, electronic configurations for atoms of different elements. In this video, we're going to look at two special cases which slightly deviate from them rules, and we're going to look at why. So I'm going to model for you the first one and how we would do the first one, and I'm going to get you to apply the same idea to figure out the other one. Okay, right, so let's have a look at the first of these elements. The first of these elements is the element chromium. Okay, so the first thing I want to do, the same as before, is we want to find out how many electrons chromium has. So we scroll up to our periodic table. Ignore this writing, this is from the last video, but here you see chromium is right here, this element, and its atomic number is 24. To us, that means there's 24 protons in the nucleus of this atom, and if there's 24 protons, that means there's going to be 24 electrons. So that's the first thing, is I write down chromium as 24 electrons. And again, if you haven't done the previous video on how to write electronic configurations, you really should pause the video, go back and watch that one first. Otherwise, this one is going to be much more difficult for you. Okay, so the next thing then, on the next line, we're going to write the electronic configuration for this. We're going to begin by writing down the symbol for chromium, is Cr, and then we're going to start writing the electronic configuration. Okay, so just a quick reminder, this is the order that we fill the sublevels in. This is the cheat sheet, or the cheat way of remembering the order. The other way is the way I showed you in the last video, to use your periodic table to figure out the order that you fill up the sublevels in. Again, I'm not going to go through that again. If you're not sure what I'm on about, you need to go back and watch the previous video. So I'm going to assume that you remember how the sublevels fill. And I'm going to start filling it. Chromium is 24 electrons. So that means we have to account for 24 electrons here. So the first sublevel is 1s, and the 1s can hold 2 electrons. So we write it as 1s2. That means there are 2 electrons in the 1s sublevel. The next then, because obviously that's only 2 electrons, we need 24. Well, the next sublevel to fill up is the 2s, and it can hold 2 electrons. Then we've got the 2p, and the 2p can hold 6 electrons. That's 10 so far. The next sublevel is the 3s, and it's 3s that can hold 2 electrons. So 3s2, that's 12. Then the next sublevel is the 3p, and that can hold 6, 3p6. The next sublevel is the 4s. And if we were following our old rules, we would have wrote 4s2. How many is that? 2, 4, 10, 12, 18, 20. We've got 4 left. So the next sublevel is the 3d sublevel. And before this, we would have written 3d4. Okay, so that's exactly how we would have done it up to now. And it's fine that you would have thought that that's how you would do it. But like I said, there's a kind of a special case here. And that special case is that it turns out that if a sublevel is half full or completely full, then that is much more stable than a sublevel which is like any other amount except half full or full. So because the 3D is made of 5 orbitals, if there are 5 electrons in the 3D sublevel, that means there is 1 electron in each sublevel. This is an especially stable configuration, okay? So that's one thing to really get right, that electron configurations are all about stability. The most stable configuration is the one the electrons will take. So in this case here, we've got a 4s sublevel, which is full, and we've got a 3d sublevel, which just has 4 in it, okay? There is a more stable configuration in this, and it goes like this. If one of the electrons was to move from here to here, what that would leave us with is 4s1, which is half full. And yes, it's full up here, so full is more stable. But now that the electron is in the 3d sublevel, it becomes 3d5. That means that this is also half full. Whereas this one before is completely just 4, is not half, it's not full, it's just nothing. There's no any level of stability there. So it turns out that this, with both of these being half full, is more stable than the 4s being full and the 3d having 4. So this element, chromium, is an element that will do this. So this here is the correct electronic configuration, and this one is the incorrect one. So this one does not exist, this top one. This bottom one is the way it is. We say an electron gets promoted, or it moves from the 4s. Sorry, I don't know what I've done there. An electron moves from the 4s to the 3d. Okay, so it moves, it gets promoted. And again, this makes the configuration more stable. All right, now notice it doesn't move from the 3p to the 4d. That never happens. It doesn't move from the 3s to the 4s. That doesn't happen. It only moves from the 4s to the 3d. Okay, now that you know how to do that, I'm going to tell you what the other element is, and I want you to do it the same way. So the first thing I would advise you to do is take down this configuration for Chromium and put a mark beside it, like I have a star, and go, this is one that we might call an exception to the general rules, or a strange one, if you like. I call them the strange ones. Strange one. And because it's the strange one, they love to ask about this in the exam. So this is a good one to really practice writing down. The other one we're going to tell you about, and it follows the same kind of idea, is the element copper. All right, so what I want you to do now is I want you to pause the video, follow the process I've just done, and figure out what's going to be unusual about copper. So pause the video and do that now. Okay, so you should only be playing if you've had a go at writing the electronic configuration for copper, and hopefully you can see that it's the same idea. All right, let's have a look at copper. Copper has 29 electrons. Okay, 29 electrons. And its symbol is capital C, small u, copper. So it goes like this: 1s2, 2s2, 2p6, 3s2, 3p6. Nothing unusual up to there. That's the same as it always is. Then we've got 4s, and we would normally have said 4s2, 3d9. That would get us to 29 electrons, I think. 10, 12, 18, 20, 29. Yeah. So if we're following the general rules, that's what we would have done. But hopefully you can see that there's a special case here, that if one electron got promoted from here to here, we would say that this is half. Okay, so at the moment, sorry, before we promote the electron, let's just clarify what's going on here. Okay, so oh, sugar, 3d9. Okay, before we promoted the electron, we would say that this is full and this is absolutely nothing. 9 is not, it's not like half full or it's not full. So it's what I'll call a random arrangement. Random. Okay, definitely not got any extra level of stability. So we've got one full, one random. Whereas if we promote an electron from here to here, that leaves us with the configuration 4s1, 3d10. Now what we've got is half full, the 4s is half full, and the 3d is full. So we see here, this is extra stability. And because of this extra stability, this is what happens. So this is the correct configuration. This is incorrect. Okay, so hopefully you managed to get that right and you see that's that idea. Again, I would write out that configuration, make sure you know that it's this one, and then I would say special case. Okay, special case, and make sure that you know those two. All right, guys, that's it for configurations. We've done electronic configurations now, and we've looked at these two special cases. In the next video, we'll be looking at the electronic configurations for something called ions. So I'll see you in the next one.